Hello, everyone. I'm Shantanu Kumar. I'm a PhD candidate at Colorado State University, working under the guidance of Dr. Mohammed Mehany. I'm going to present about one of our research on conceptual framework for transportation infrastructure resilience optimization. This is the agenda for our presentation. It starts with a little bit of background on transportation, going over the methodology of this research, and followed by results and conclusion. Um, a little background on US transportation here. The US transportation industry accounts for about $7.7 trillion in value, which is about 9% of US GDP. Over the years, the rehabilitation backlog in transportation sector has increased to billions of dollars. And this problem has been compounded by the frequency of disaster occurrence, leading to massive recovery costs. There is definitely a need for resilience strategies when rebuilding after a disaster or when constructing new transportation projects. The limited financial resources and the increased demand for transportation infrastructure maintenance and rehabilitation will always be of concern in the transportation sector. Therefore, we need to promote resilience thinking, and infrastructure rating systems are a good way to do that. For instance, Envision rating system, which is one of the most popular and widely used in the United States, promotes sustainability and resilience, and that would be one of our uh, considerations in our research. A little bit of background for previous research studies. In 2000, Todini found that there was a direct correlation between resilience and investment. Uh, However, in 2010, Berkeley contradicted that by saying that more cost effective options or investment options can be used to achieve a higher resilience. This thought was echoed in 2012 by Goodman, where he found that there was a trade off between investment and the level of recovery. Level of recovery was just one of the dimensions of resilience. In 2018, Ton and others used a qualitative approach in identifying barriers to improving resilience. We saw that a lot of previous studies have accounted for resilience comprehensively. However, there's definitely a room to explore the trade off between investment and resilience further. And that is why we proposed solve the cost resilience trade off using a quantifiable approach. The objectives of this study are to minimize the cost and to maximize resilience. It starts off with research problem formulation, as we saw in the last slide, goes into the specific trade off of cost and resilience. And resilience has been denoted by the Envision resilience credits in this research study. Uh, After that, we created mathematical equations for both the cost and resilience variables. Uh, Used Python 3.5 to code our optimization functions and used exhaustive search in our preliminary studies to get the optimized solution. Thereafter, I'm going to go over the Envision resilience credits here. There are 6 of them, and in our preliminary data set, we suggested 4 different combinations for each of those credits. Each of the combination was a set of different strategies. For instance, let's consider a river crossing project. One of the combination can be one of the strategies in one of the combinations can be improving the cross river mobility. Strategy 2 can be improving the natural flow of river. Strategy 3 can be reducing traffic flow congestion. And strategy 4 can be integration of the project into existing roads and highways. So these 4 strategies can account for one combination. A set of these combinations are pertinent to each of those credits in the Envision Resilience credit section. This was the mathematical formulation for cost and points function. We can see that the summation ranges from 1 to 6 because there are 6 resilience credits, and the NC1 just ensures that one combination is selected for each of those resilience credits. For this particular mathematical formulation is subject to various constraints. The project budget is one of them. The total number of resilience credits, which is 6, is another one. Number of combinations per resilience credit was another constraint, and the last one was one combination per credit was to be selected and added. The next One is the objective function. So we combined both the variables by normalizing them, and we ensured that the user-defined importance factors were also normalized. We can see that WC here represents the relative importance factor for cost, and WP represents the same for number of points. They are subject to the constraint that the total project cost should not exceed the approved budget. One thing to note here, the negative sign here and the positive sign here. The negative sign denotes that when this objective function is maximized, the cost will be minimized and the points will be maximized. This is analogous to the fact that when we have a series in ascending order, when we put a negative sign to that series, the series becomes descending, right? So that's just an analogy to help explain this objective function. This is the preliminary data set here. There are 6 credits, as I told you, and the combinations were 4 for each of the credits. Each combination has their respective cost and level of achievement, and level of achievement just shows the level of resilience, if you will. In total, there are 4 to the power 6 options, which equates to 4,096 total options. And that is why we use exhaustive search to find the optimized solution. In scenario 1, we tried to minimize the cost, and that is why the user-defined weightage was 9 for cost and 1 for points. For scenario 2, resilience was maximized, and that's why points had the highest user-defined weighting. And scenario 3, both cost and resilience were optimized. That is why both received the highest rating. And here we have the optimized combination for each of the different credits in Envision. This is just the summary of all the results. The budget was $110,000. The maximum achievable points was 74. In the first scenario, when we were trying to minimize the cost, we got the lowest possible cost here, $102,500. When we were trying to maximize the points, we got 74 points, which was the same as highest achievable points. And when we were trying to minimize cost and maximize points, we got total cost as $108,000 and total points as 74 points. And in conclusion, I'd like to say that the optimization model was successful amidst budget constraints. The model is highly dynamic and adaptable to future versions of Envision. And using Envision actually provides a really good baseline for resilience assessment over various geographical regions. This optimization tool is definitely having some potential to be converted for industry use. For future, this model can be adapted to future versions of Envision. Right now, it's only catered towards Envision version 3. As the complexity increases on this model, the evolutionary algorithms can be used. And right now, we are working towards different dimensions of resilience and infrastructure interdependencies to be accounted for in this optimization model. Here are a couple of important research studies that we have cited. And if any of you have any questions, comments, and feedback, I would love to hear from you. There is my email, shantanu.kumar@colostate.edu, and I've attached a QR code for my LinkedIn profile as well if you would like to connect. Thank you so much. It was a pleasure presenting virtually, and thanks a lot to Dr. Tom Latham and his team for organizing this conference virtually. I'm really grateful for that. I hope you guys are staying safe, and thanks a lot for watching my presentation.